Oh man. Good morning, everyone. It has been so long since I haven't seen many of you.
Good morning.
Hi. Grace, hi Claire, where's your sign there from? That's kind of funny.
I have no idea. I just find these things on the internet, for better or for worse.
So how was the least spring break of spring breaks for people?
I had so much work, and then I had a panic attack because I went to check when the basin lab was due because I couldn't remember if it was due at like 11 or and then I saw Sunday and that's all I saw, and then I panicked before I realized it was the 19th, not today.
Yes.
Or yesterday.
Yes.
Because I checked it this morning. So
I think verbally I told you guys one date and then wrote a different date on Blackboard. So the date I wrote on Blackboard was the 19th. So honestly, I don't care. The 19th is fine.
Yeah. Well, also I probably misheard you. It's much more likely that I misheard you than you misspoke.
I'm pretty sure I said that. Like because in fact, Maya sent me an email asking me when it was due, and I was like, it's due today. And then I looked and I'm like, that's not what I wrote here. So it's not due today. So it's good. Everything's good. And then Henry had a question too that I intentionally did not check work email for a couple days. And so I missed Henry's email too for a couple days. So it all worked out. It's all good. Did anyone do anything fun?
No.
Silence. So Barone and I, hi Lauren. Lauren, I don't know that Gabby is going to be here this morning. She got a job at Home Depot and she's filling out paperwork.
She said that she would show up late. So
okay, cool. Okay.
I'm just gonna chill and learn.
Sweet. All right, very good.
You're going to be an honorary geologist by the time this is over.
It's true. You should earn course credit.
One benefit about being an interpreter, except I never get the certification.
That's true. You get to learn lots of things. So Barone and I met in Mendon Ponds with face masks, and we recreated the Mendon Ponds field trip. And then with a GoPro camera, which I had attached to my head. And then I spent like 2 days like compiling all of that and editing it. And it's pretty hysterical, I'm not gonna lie. That was the most fun thing I did over break. Everything else was bleh. I also did not finish your tests. So I got most of them done. I have a couple left to do. Most of you answered the survey questions for extra credit, but not all of you did. Don't forget those are on Blackboard, and I'm pretty sure that's due today. So it's not arduous, and they're for bonus points that really just go in your lecture grade, but if it makes you feel better to think about them as going on your test, then think about it that way if you want. But I think most of you completed that. I sort of saw that Krakatoa erupted, Danielle. Was it a big one?
I think it was just like lava flows, but there was like a couple other volcanoes that in Indonesia that went at the same time.
That's kind of fun. Earth is sick of us. You're taking out one person at a time. So I want to show you guys something quick, and then let's see, what's the first thing I want to share? Not that. Oh, I certainly don't want to share that. Give me 1 second. Oh, I cannot minimize Zoom. Okay, that's fine. I can minimize this though. Escape. And then head to this email thing I got today. So you guys should have received, I don't know if it was an invitation or what to, where's that screen? Why can't I share that screen? Now it'll let me see. To join something called CircleIn. Can you guys see CircleIn now?
Yeah.
Okay. So basically, CircleIn is something I'm supposed to have nothing to do with. It is basically a place for students to collaborate virtually. And so there's apparently an intro for faculty that I have not watched yet. I've just read all the stuff. So you're supposed to be able to go here with like a fellow student and like, so let's say you're studying for a test or you are working on an assignment and you want like a space, a virtual space to be able to do that. I think you're supposed to be able to do that now, and you should have gotten an invitation sent to your MCC email. And the fun part is that you can win prizes and earn points for doing it. So some of you might enjoy this, some of you may not, but there it is. So I have rolled this out to you. Do you guys have any questions? I probably don't have the answers, but I can find them.
Like points in general or points towards like our grade?
Good question. Points in general, which I feel like you can use for like gift cards.
Okay.
Okay. But yes, no, not points for your grades. That's a good question. Any other questions? Okay. So certainly by next class, the grades will all be up, not just most of them. And that'll be fun. What can you guys see where it says the Proterozoic eon now?
Yes.
Yes, thank you, Dayton. Cool. So at this point, we're starting Unit 3, and Unit 3 begins with the Proterozoic eon. So just as a recap, at the end of the Archean, the oceans were no longer acidic. The air was still mostly anoxic. So in terms of oxygen levels, there were organisms that were starting to pump oxygen into the atmosphere. Do you guys remember what those are called? They're so fun.
Stromatolites?
Yes, very good, Danielle. Yes, those are called stromatolites. And so stromatolites are super cool, and they have sort of a tragic story here. So stromatolites, it's like I haven't done this in a week and no longer remember how to do anything. So that's convenient. So stromatolites were these, like, they're basically like blue-green algae or cyanobacteria, and they still exist now. And they evolved, and they were the first organisms to kind of figure out how to, I'm moving things around, I'm not distracted. They were the first organisms to figure out how to take all this carbon dioxide that was in the atmosphere in the early Earth and convert it and use it as food. And that's actually one of the things that we'll see in the next unit, especially, is that the organisms that end up surviving are the organisms that figure out how to take trash and turn it into treasure. So that is true of stromatolites. And so they begin the process of creating oxygen in the atmosphere, and they're basically like the first simplest. They're not even really plants; they're bacteria, but they figure out photosynthesis. So they begin to pump oxygen into the atmosphere, which is going to like completely change the Earth. At the end of the Archean, it's maybe 1% oxygen in the atmosphere now. Or atmosphere. Do you know how much is in the atmosphere now in terms of oxygen content?
Is it 98%?
It is not.
Is it like 10?
It is more than 10 and less than 98.
I'm like 14 though.
It's
16.
like 21. It's like about 21% oxygen right now. So at the end of the Archean, it was like 1%. And the 1% was due to the stromatolites. And so what's kind of crazy, and we'll see in the Proterozoic, is that, and if we were in class, I would, and I've done this every year, like I put stromatolites around the room and I make everyone sketch a stromatolite in their notebook, because they're literally the organisms they're organisms that changed the course of the Earth. Once oxygen started to build up, which took a really long time, because so we go in the Proterozoic from about 1% oxygen at the beginning to like 20% oxygen or so at the end. And it takes 42% of the history of the Earth for that transition to happen. But once that happens, like, holy crap, it allows life to just flourish and become way more complex, and figure out new ways to create energy, to utilize energy. And evolution just like explodes, and all of that happens because of oxygen. And the oxygen is, all of that happens because of the stromatolites. So the tragic story of the stromatolites is that once they create all of this oxygen, what happens is that the organisms that evolve as a result of the stromatolites, like, they end up just taking over everywhere that the stromatolites live for the most part. And they're more successful than the stromatolites. They start eating the stromatolites, and the stromatolites today still exist, but they only live in like hypersaline lakes where nothing else can grow. So they created this environment where all of these other life forms could flourish, but by doing so, basically relegated themselves to like the saltiest, driest, crappiest places on the earth, which I think is a great story. And that's why I make everybody draw stromatolites. So we'll talk about them more later on in the semester. Ooh, do you guys have any questions about stromatolites? They're pretty great. Are you ready to start talking about the Proterozoic? Silent. Woo. Yeah.
Yeah.
Yeah. All right, let's do this. Okay. So the Proterozoic is 40% of the history of the Earth. So in order to break it into more manageable sections, geologists have subdivided it into 3 chunks. So there's the Paleoproterozoic, which means old Proterozoic. And then there's the Mesoproterozoic, which means the middle Proterozoic. And then there's the Neoproterozoic, which means the newest Proterozoic. Does that make sense? Yes.
Oh, yes.
Thank you. Cool. So the Paleoproterozoic is the oldest part. It begins about 2.1 billion years ago. And it's characterized by a couple processes. One of the most important ones is called continental accretion. What do you think that means?
Continents are being formed by subducting plates secreting their material onto the upper plate.
Right. Yeah. So remember that accretion is like the adding on of stuff. So like if you had like a lump of Play-Doh, right? And then you had a little more Play-Doh and you stuck it to the side and you just kept building bigger and bigger chunks of Play-Doh made up of little bits of crap of Play-Doh. So it eventually grows into a big blob of Play-Doh. So that's basically what happens during the beginning of the Proterozoic. And so this is a paleogeographic map of North America, or what geologists call Laurentia, during the Paleoproterozoic. So a couple things. So let's take a second and look at this map. What you can see here, first of all, is that north is actually like, it's, you kind of have to tilt your head here, because north would be to the left of this map. So Rochester is like right there, right? So Rochester is south of the equator during the Paleoproterozoic. You can see that there's still sort of like an elevated, there's like a sort of a mountain range at that point. There is an island chain here also that you'll see. And North America is often called by geologists Laurentia. Laurentia is basically a big old plate. And based on sort of the distribution of landforms, Laurentia includes all of North America. It also includes Greenland, so you can see that there. Scotland and some of Scandinavia. So during, a lot of times when you're reading about the last ice age, they will call the last ice age, they'll call the ice sheet at the last ice age the Laurentian ice sheet. You'll learn that there's other chunks of craton that that are combined to form Africa, and we'll get to some of those names later on. Do you guys have any questions? Let me make sure I have the chat open so I can see y'all if I need to. Where are you, chat? It's open somewhere. Okay, maybe it'll just pop up. All right, so One of the first bits of evidence for continental accretion is something called the Watmay origin. A lot of the rocks that we're going to be talking about in this chapter are in Canada, which is where the oldest rocks in North America are located. So the word origin should sound familiar to you. What do you think that might mean?
It's a mountain building event.
Yeah, it's a mountain building event. Okay, so the Watmay origin is located here on this map. So one of the last things that we talked about with the Archean was this idea of granulite greenstone belts, right, that grow into these provinces. And what we're going to learn about today is that these provinces smashed into each other. And when they smashed into each other, they formed mountains. And I feel like there's definitely a handout in here that I gave you that you'll see on just the next slide. So the Slave Province is an example of one of those chunks of granulite greenstone belts that combines to form a province. And then the Slave Province became accreted onto Laurentia here in what's called the Watmay origin, which is dated at about 1.9 billion years ago. The Watmay origin rocks are kind of cool. They're actually our oldest evidence for a Wilson cycle. Do you guys remember what a Wilson cycle is?
The opening and closing of ocean basins?
Yes, and I want someone else besides Grace to answer the next question. Yes, that a Wilson cycle is when ocean basins open and then they close too. So the opening of the ocean basin is evident. You look for evidence of divergence when you look at rocks. So here is, and take a second to look at this. This is this is a cross section of a model of the Watmay origin. So in the Paleo-Proterozoic, you have opening and then closing of very small ocean basins at this point. What evidence do you see in this diagram for divergence? There are several.
The stretched Archean crust.
Very good. Yeah. Good. So way down here, you can see stretched Archean crust. Remember, the divergence is like the stretching of crust. Good. So what sort of things happen when crust stretches? How can you tell that the crust is stretching?
The rifting.
Henry, yes. Henry saw that there's sections down here about rifting. So rifting typically creates normal faults. Normal faults are ones where the hanging wall slides down. And that's what we see here in some of the stretched Archean crust. So there is normal faults caused by extension or stretching of the crust. And then the other thing we know is that when we stretch the crust, what does that sometimes cause?
Decompression melting?
Great, Grace. Yes, it causes decompression melting. So the crust gets thinner and thinner and thinner, and that induces or causes melting in the crust. It causes melting, which typically is basaltic in composition, because basalt is, if you think of ocean crust is really thin. When you start to rip apart really thin crust, the first stuff that rises in really thin crust is going to be mafic in composition. So if we looked at the stretched Archean crust, we see not only basalt flows, but we also see some, boom, I don't know why I did this, some normal faults also. So then if crust is ripped apart into two segments and then separates so that you have an ocean basin in between, how do you think that explains the presence of the sandstone and then the carbonate rock here? It looks like a dolostone here. Why do you think you would have, if we're stretching into two chunks of continental crust, why would you anticipate there being, and there's more divergence, sandstone overlain by carbonate rocks? Where's that sediment coming from? So think about this. We have a big old continent. It's not that big, but let's say we have a reasonable sized continent, and it starts getting stretched. And when it gets stretched, it gets thinner and thinner and eventually separates into two chunks. What's still happening to that continental crust while it's being separated?
It's still being accreted?
It's not accreting right now because it's being split, so it's not accreting. But what is going to happen to any sort of continent that is above sea level on the Earth? What happens to all land above sea level?
Erosion.
Yes, thank you, Danielle. So it's still like eroding. So you have two chunks of continent and they're still eroding. So on that stretched Archean crust in between here with the normal faults and the basalt flows, we have sediment that is shedding from these two continents. And that's where the sandstone comes from. As those continents get further and further away, this stuff in the middle is now further from the source area, right? So we're not going to get sandstone when the source areas are farther away. We're going to start to get siltstone and then or shale and then limestone. So the carbonate rocks, the succession here is first you have normal faulting, then as it starts to pull apart, then you have volcanic activity. When it separates into two chunks, you start shedding sand. And as those two source areas get further and further away, then you start depositing carbonate material. And that explains the sequence that we see here.
Is there infill with like a sea or something to deposit that?
Yes, that's what the sandstone is filling in. It's filling in a sea. Good. So
where does the water come from that? Like,
it's just like the lowest lying area. So sea level will just drown whatever becomes low lying to whatever sea level happens to be. So sea level at this point, if you can think of that as being stagnant, but then as the crust gets thinner, it starts to subside in elevation. So the water just inundates whatever is low lying. That's a good question, Henry. So an example of that would be like the Red Sea. Let me pull that up real fast. Google Earth. There we go. Maybe. I'm having my computer do a lot today. Can you guys start to see Google Earth pop up or no?
Yes.
Thank you. All right, so as we pop over here to the Red Sea, so the Red Sea used to be a low-lying area where the Arabian plate was pulling away from the African plate. But once this little thin area here near Djibouti, which is my daughter's favorite country, I never knew where it was located. I'm such a heathen. Once that started to separate, connected to the Gulf of Aden, the ocean rushed in here and formed the Red Sea. And what's cool about the Red Sea is that this is like some of the youngest mid-ocean ridge on the Earth. And this is like one of the youngest divergent plate boundaries, which is extending all the way up here. And then also kind of extends down here through these series of long, narrow lakes that you see here in Africa. So these long, narrow lakes are examples of divergence. Right now there's sediment shedding into there, but eventually when it connects to the ocean, when it gets down to Mozambique, then the ocean will rush in and create this large linear sort of sea. Does that make sense?
That's wild.
It's crazy. All right, so your evidence for divergence is initially rifting of the Archean crust followed by deposition of sediment from the surrounding sources like there. So you know what else is cool here? This is the first time in the geologic record that we've ever talked about carbonate rocks. So if we have carbonate rocks that are depositing, what does that mean?
The sea's not acidic, or
Yes.
it's much less acidic?
Yes, that is absolutely true. So the acidity of the Paleoproterozoic ocean is way lower, right? We start to have water that is alkaline enough that carbonate doesn't completely dissolve as soon as it flows in. It's very cool. Cool. So Wilson cycle is a two-part cycle, right? So you have stretching and divergence, and then that's followed by convergence, and that's going to be what's forming the mountain building event, the origin portion of it. So that ocean basin that opens then closes up, and we can see that in the rocks here. So this is a cross section of the Watmate origin, and what you see here are two chunks of continental crust that have collided. So you, along the zone of collision, that's where you have your metamorphic rocks, where the temperatures and pressures were highest. As you get away from the temperature and pressure, like most intense section, you get some cool faults that I don't think we've talked about. We haven't talked about in this class, but actually this is great because we're going to talk about them in lab today. So in these faults, we have faults where the hanging wall is moving up. So what would we normally call a fault where the hanging wall is moving up?
Reverse fault?
Yes, we would normally call it a reverse fault, which is the result of compression. So those shelf sediments, the sandstone and the carbonate rock, gets folded and faulted not only into reverse faults, but also into something that is new called a thrust fault. Let's see, I would like a pen. And there's a typo here. Thrust fault is actually 2 words. So a thrust fault is important for today. A thrust fault is a low angle. This is angle. Reverse fault. By the end of the semester, I'm actually going to be able to write on the screen like this. So we're talking about less than like 30 degrees. And the angle that I'm talking about is here, where the thrust fault intersects with the surface. So this angle here is less than 30 degrees. That's all a thrust fault is. It's really common when you have continents that smash into each other. You have the basement that is below, and then that's like this crystalline mauve colored material here. And then you have sort of the sedimentary rocks above, and those they just kind of like crinkle like on top of one another. And sometimes they'll form reverse faults if the angle of the fault is steep, and other times they'll form thrust faults. Thrust faults, again, super common in continent to continent collision. So our evidence for convergence is metamorphism in the most intense zone of convergence. And then as you get a little bit further away, you see folding and faulting of some of those sedimentary rocks, which is actually like a model that works not only with the Watmate origin, but it works when we're going to be talking about the Appalachians in a couple of weeks. And you see the same exact sequence there, where at the zone of most intense convergence, you get metamorphism, followed by thrust faulting when you get further away. So it's nice when like things are consistent. That's a cool thing. So this is the way that the Watmate origin rocks look today. And within it, we can find ancient evidence for normal faults and for basaltic lava flows. And we see that same model also with the breakup of Pangaea also. So these observations are consistent regardless of whether we're looking in northern Canada, whether we're looking in the Appalachians, whether we are looking in the Himalayas. You see the same pattern. Cool. Any questions? Are you okay, Jenny? Did you sneeze? Okay, good. All right, good stuff. So I just wanted, it's not important that you know that the Hudsonian origin is another origin that is slightly younger. It's 1.5 billion years ago. What I just want to show you on this slide is that there are several examples of these origins that stitch together these Canadian provinces. Not like the actual Canadian provinces in Canada, but the Archean provinces of crust are stitched together in these origins. So if you look at this map here, here's where the Wapme origin is, and it helped to build to connect the Slave province to Laurentia. Here's the Hudsonian origin, and the Hudsonian origin stitched together the Hearn province and the Superior province. And you can see that here too in Hudson. So this is just a cleaner map, but regardless, illustrates the same thing, that these Canadian provinces, these Archean provinces are stitched together in Canada with several origins. And this is how basically we're taking our chunks of Play-Doh and we're adding them together to form Laurentia. Cool. You guys have any questions? Oh boy. Okay. All right. So that happened in the early Paleoproterozoic. You have the building of continents. The other thing that you have the first evidence for is the first ice age, perhaps, about 2.6 to 2.1 billion years ago. And the rock layer in Canada, which preserves evidence for the first ice age on Earth, is called the Gogan deformation. And here's a picture of it. Well, just kidding. Here's a picture of it. So the Gogan deformation is basically composed of two types of rocks that are collectively known as glacial varves. The Gogan deformation is composed of layers of conglomerate and layers of shale. And the shale layers have very thin little layers, which are called laminae, so they're laminated shales. So we see this in rock that's 2.6 billion years old, but we see the same exact sequence in rocks that were deposited during the last glacial period, which are called glacial varves. So these have been interpreted, these conglomerate shale layers have been interpreted as ancient glacial layers 2.6 billion years ago. So when you look at the layers in the bottom photo, you see that there's thicker layers, and then which were deposited during the summer. Whoops, I'm going the wrong way. And the reason that the thicker, coarser grained layers are deposited during the summer is because rivers are flowing during the summer. Rivers are dumping bigger sediment into the ocean, right, during the summer. During the winter, the discharge of rivers is way less from continents, and that's because there's so much snow, and so much water is being held and stored on land in the form of snow and ice. So during the winter, there isn't as much sediment that's deposited, and what is deposited is in very sluggish moving streams. Sluggish moving streams carry really small particles, which are like clay-sized particles that then form shale. So the thinner layers are the shale. Those represent winter deposits from streams. Collectively, this is called a varve, and it basically just shows seasonal variations. So just to confuse things a little bit more, is these glacial varves, these packets of conglomerate and shale, alternate with what are called tillites. What does the word tillite make you think of?
Till?
Glacial till. So someone who's not Grace, Tell me something that you know about glacial till, besides that it's dumped by a glacier.
Doesn't it sort itself, kind of?
So it's actually not. It's the opposite of that, but I like the way you're thinking. So till is unsorted. It just means dumped by a glacier. It's not sorted by water at all. So you have a ton of different grain sizes. It's very poorly sorted. The opposite of till is actually called stratified drift. Stratified drift is deposited by meltwater. So that will be sorted by size, because when water starts to slow down, it'll dump particles of a certain grain size. When it slows down more, finer grain sizes are deposited, and so on and so forth.
I was thinking S-curds.
Oh, okay. That's cool. That makes sense.
Makes sense.
It does, yeah. Okay. So, so the tillites represent a time period when glaciers bulldozed over the land and they just left behind this disastrous rubble. Totally unsorted stuff that sometimes, like when we went into Mendon Ponds, sometimes that till can be like shaped into drumlins, but it's till. The glacial varves represent glacial lakes. So the glacial lakes are fed by streams. And the streams are sometimes fed, we know, by summer, by streams moving through the summer, sometimes during the winter. When you look at this section of the Gogan deformation, this material down here is a tillite. This represents a time when glaciers advanced over the land and deposited all this rubble. When the glacier started to melt back, it created a ton of meltwater, and that meltwater formed a lake, and that is what all of these varves are. They're just lake layers. So this is telling us that we have a glacial advance that is then followed by a glacial retreat, and that's why we get the varves. So when you have tillites and varves, the tillite tells you this is an advance, the varves tells you it's a retreat because it's making a ton of meltwater and therefore a bunch of streams. Cool. So we have the first evidence for that 2.6 billion years ago. And that is not random. All of this comes back to stromatolites. So what do you think? So if the atmosphere at that point in the Earth is only 1% oxygen, what's the rest of it, do you think?
Carbon?
Carbon, but how, ooh, what just happened? But how is that carbon, like, it's not just carbon floating around. Oh, I didn't go.
Methane?
Methane, good. Methane and what else?
Carbon dioxide.
And carbon dioxide, good. So both of those are greenhouse gases, right? So when you have lots of methane and carbon dioxide, it's really hot on the Earth. But for stromatolites, like, this is ideal, right? Because there's all of this carbon dioxide and all of this, so it can just suck up all the they can suck up all the carbon dioxide. When you remove carbon dioxide from the atmosphere, what do you think happens to the temperature?
Decreases.
Yeah, it decreases. So greenhouse gas is like a blanket. So you know when you go to bed at night, you throw a blanket on to keep warm. Does a blanket make you warm?
No.
No.
Good. Well, the blanket just traps your own body heat, right?
Yes.
The more greenhouse gases that you have, it's like the thicker the blanket. So when you get rid of some of the carbon dioxide, that's like taking off a blanket. So you're not going to be retaining as much heat. So drawdown of the carbon dioxide in the atmosphere because of the stromatolites actually makes the world colder, which likely led to the first ice age. And that led to what's called the Great Oxygenation Event, or catastrophe, depending on your perspective. Because someone's feast is someone's famine. So what the Archean stromatolites did was they created free oxygen in the atmosphere. The first thing that happened was when those cute little stromes were pumping out oxygen into a world that had almost none, is the first thing that happened was those rocks, those Archean rocks, which, remember, we saw that picture of the conglomerate, and it had pyrite, and they were like rounded grains of pyrite. Well, in the beginning of the Proterozoic, those little grains of pyrite started to oxidize. All of the iron-rich rock started to oxidize. The whole earth, the whole surface of the earth was covered with iron-rich rock, which, as the stromes were pumping out oxygen, that iron started to oxidize. And we're gonna actually start class talking about this next class, but this is super cool. So the first evidence for life on Earth begins about 3.8 billion years ago. And this bottom scale is age in billion years. It's also backwards. Well, it's not really backwards, but here's today. Here's the Earth a billion years ago, 2 billion years ago, 3 billion years ago, and then 3.8 billion years ago, which is when the first evidence for life on Earth occurs. On the y-axis here is the partial pressure of oxygen in the atmosphere. So right now, oxygen is about 21%. 21% is like 0.2. So that shows where we are today in terms of oxygen. Now there's a red and a green curve on here. We can all agree as scientists about the composition of the Earth today, of the Earth's atmosphere today. But it varied, and models and estimates vary when you go back over time. So this red curve is the high estimate for what geologists think the pressure, the amount of oxygen was in the atmosphere. The green curve is a low estimate. So here's where stromes first evolve, and they're hanging out. They're doing strome-like things. And for this whole time, all that's happening on the Earth is that stromes are just creating just a touch of oxygen, just a touch. And it doesn't start to build up here until about 2.5 billion years ago. And then it starts to build up. This is the crazy part for me. So here you can see that regardless of whether you're talking about the high or the low estimate of oxygen, it's low, but it just remains steady. And this is like a billion years of Earth history, right? All that's happening for a billion years here is the Earth is rusting, like literally for a billion years. Stromes are pumping out oxygen, and it is oxidizing the iron-rich rocks that are present on the surface of the Earth. It is just rusting of the Earth.
Is that why Mars is red?
Yes, yes. They also had like a runaway greenhouse climate, and yes, and all of the oxygen that was existing in the atmosphere was reacting to the rocks on the surface. So this oxidation of iron-rich rocks, as well as a process we're going to talk about in the next slide, creates what are called banded iron formations, or BIFs. BIFs are fantastic. So like 90% of all of the iron that is still used commercially on the Earth still comes from banded iron formations, which literally only formed in this billion years, from 2 to 1 billion years ago, is when BIFs form. And it's because the whole Earth is rusting, which is crazy. So we're going to do an assignment where you guys look in small groups at this curve and you answer a couple of questions next class. And I feel like I handed you a paper with this curve on it. So if you
did.
Okay. So make sure you have that for the start of next class. We'll open next class doing that. All right, cool. So let's talk about banded iron formations because they're pretty sweet. So banded iron formations, or BIFs, look like this when they are cut and polished. They are beautiful. We have a couple BIFs on campus. The guy who taught this class before me was about 100 years old. And people used to joke that he was around for the formation of BIFs because he looked like Father Time. And so one of the worst days, but I was so glad it wasn't me, was when he was carrying one of these BIFs in a in a box and just dropped it, and it like broke into like 1,000 little baby Biffs. And I was like, no, but then I'm like, well, better him than me. That's good. So Biffs form on the Earth between 2 and 3 billion years ago. And they are layered, as you see in this picture. So this picture down below here, this is taken at the Museum of Natural History in Manhattan, which no one can go to for a long time. And this one, I believe, is from like Minnesota. So most of the red layers that you see here are hematite. Here's the chemical formula for hematite, Fe2O3. Some of the other iron-rich minerals that you have in Biffs are magnetite, which is Fe3O4. So you can see, right, chemically, this is iron and oxygen. This is oxygenated iron. So that oxygenated iron, the iron is found in the seawater floating around in the surface of the sea. It reacts with oxygen right along the surface of the sea, and it turns into hematite and magnetite, and then it falls to the seafloor. And PPT stands for precipitates. It precipitates on the seafloor. So I'm going to show you a 3-step model. Ooh, and so in your packet of papers that I gave you before you left, I gave you a couple handouts from this chapter. So it's a white paper, and on the front, you see this is the Watmay origin. That's that handout there. And then on the second page, there's 2 curves. There is the fun little oxygen stages curve, and then there is the diagram I'm about to show you for banded iron formations. Okay, so during the summer months, the rivers on the continents are going to erode, and they carry the products of that erosion, sediment. They carry it down from the source area and they dump it into the ocean. So one of the things that the river is eroding is really iron-rich rocks. So that iron-rich rock gets eroded from the continent and dumped into the ocean. What happens is, and this is happening because it's summertime, so there are lots of rivers, lots of river discharge, is that iron in the surface water is going to react with the oxygen that those cute little stromes are making. And it forms magnetite and it forms hematite. And those are solid particles and they're relatively dense. So they will settle through the seafloor and accumulate in a layer on the seafloor. So then when it's cold during winter time, those rivers, the discharge is going to go way down, right? Because again, you're going to have snow and ice storing water on land. So those rivers stop shooting in a whole lot of iron. What was already in the seawater, though, was some silicon. And we'll explain where the silica comes from. But the silica accumulates in a layer, basically, if you want to think about the rivers as being turned off during the winter. So when the rivers are turned off, what forms is a layer of silica, usually in the form of chert. Because not only are the rivers flowing less in the winter, so the discharge is low, but the other thing is that photosynthesis, we know, slows down significantly in the winter because there's less sunlight getting through the Earth's atmosphere. So there's not as much oxygen. So without oxygen, the iron and the oxygen aren't going to react. And so instead of that layer of hematite and magnetite, instead you're going to get a layer of silica, which is typically found in the form of chert. So these are, the next 2 things here are rocks you haven't heard of yet. Cherty limestone and cherty shale. There's nothing really exciting about them. There's just limestone with some chert mixed in, or shale with some chert mixed in. That's really all it is. The source of chert, though, is important. The source of chert is volcanic eruptions. So volcanic eruptions do not just happen in the winter, right? Volcanic eruptions happen year-round, but you don't have the deposition of iron happening year-round. So by and large, what will be deposited during the winter is, because there's no iron settling, it's really just silica settling. Then when the temperature warms up again, photosynthesis gets back into gear, and you also have river discharge that starts to increase again. Then you'll get your next iron-rich layer of magnetite and hematite that get deposited. So through these seasonal winter-summer layers, we have the accumulation of iron-rich sediment, silica-rich sediment, iron-rich, silica-rich, and these are interpreted as seasonal deposits called banded iron formations, like you see here. Yeah. And that's where we're going to stop for today. What questions do you guys have? Are you all doing well? I got like 3 emails from people who are being COVID tested like today. Are you guys healthy? Are your people healthy?
So far.
Good.
Healthy so far.
Good, good, good. Are you getting like just tired of being in the house all the time?
Oh, for sure. Especially with my family. It's like, listen, I just need some space from you now.
I hear you for sure. Cool. All right, guys. So let's take a break. Everybody get away from a screen for a little bit if you can. And we'll come back at 1 o'clock and we'll talk about structural geology, okay?
Sounds good.
All right. You guys take care. I'll see you in a little bit.